Hello everyone, I'm Aida Siala, an architect, BIM consultant and computational designer. I'm a postdoctoral researcher at Tunis National School of Architecture and Urban Planning. I'm delighted to participate with you this year in the BIM Coordinators Summit, which I reached last year and allowed me to follow new modeling, coordination and management practices closely. So thank you for organizing this annual meeting and long live the summit. I will be honored to close this session by discussing the potential of computational practices to automate and optimize coordination tasks. It's based on the students' feedback on the first promotion of the BIM Professional Master's degree in Tunisia. They were trained in computational design and were called upon at the end of the semester to develop algorithms allowing them to automate repetitive modeling, verification, and control tasks they face daily. The students were professionals with 2 to 15 years of experience. The introduction of industrialization to the construction sector has led to the adoption of building information modeling as a collaborative working approach. BIM is used to create and manage construction projects by combining all project information into a digital model. All stakeholders collaboratively develop this model, serving as a centralized hub of project information. As the utilization of BIM has advanced, it has brought about the standardization of project information and enabled the incorporation of an increasing amount of data into the model. This information holds significance as it permits analysis of factors like time, cost, sustainability, and more. However valuable and beneficial it may be in enhancing the project, this task has become laborious and repetitive. This is particularly true for extensive BIM projects encompassing intricate designs, documentation, and multifaceted communication workflows. In such tasks, BIM tools only show limits to opening large files for data extraction, uh, exporting a large amount of data for analysis, checking models' content, generating quantity takeoff data, etc. What makes every BIM process susceptible to many threats, like missed deadlines, costs, overruns, low productivity, and inaccuracies. In this context, the solution lies in task automation, which is pivotal for surmounting these challenges. It offers the following advantages: expediting repetitive tasks, hastening the design process, boosting efficiencies, enhancing operations, and ultimately elevating productivity and performance. This diagram shows the time savings achieved through task automation during the design phases, exceeding 40%, which is a huge time saver for designers, BIM coordinators, and managers. However, before delving into automation, it's essential to grasp the concept of automation and recognize the reasons behind its necessity. Automation of tasks involves establishing procedures that are customizable for all functions that are repetitive and time-consuming. The key takeaway is that this particular configuration can be applied across numerous other projects, thus making it an influential tool for diminishing execution durations. As I mentioned earlier, I draw a connection between this presentation and the feedback received while instructing task automation within the BIM Master's program in Tunisia. This was particularly evident in the computational design course. Here, students were initially introduced to parametric design, equipping them to craft intricate forms. Subsequently, they delved into employing parametric design for data handling and task automation. Regarding the tools used, our primary focus in this year was Dynamo and Revit. In this training, students were introduced to the different methods allowing them to quickly access the project parameter values by selecting elements in the model and getting elements by category or by type, to quickly change their parameter values, to import, export, and structured data so that it can be used later. Also, to automatically add new custom parameters, to compare and analyze parameter values, and finally, to graphically display the analysis results on the model. This example shows the results of verifying the compliance of program area, where compliant rooms are displayed in green and non-compliant rooms are displayed in red. To access their learning outcomes, students were tasked with leveraging the skills acquired in class to develop customized algorithms to automate the most frequently encountered repetitive tasks during their professional activities, the nature of their discipline, whether architecture or engineering, and their specific roles, encompassing design, modeling, coordination, or management, shaped these tasks. Based on the specific tedious tasks encountered, the issues defined by the students were original and the proposed solutions provided were innovative. Next, I'd like to share a few problems that were identified along with the corresponding solutions that were put forth. The first proposal concerns developing a process allowing BIM coordinators to automatically create all model views at the project's beginning according to the BIM Charter and share them with all stakeholders so they can work on the same support. This process is based on two case steps: entering views and sheets data in a single Excel file, and importing data to automate the creation of all views and sheets with all their parameters. Here is an example of running the script. As you see here, at the beginning, we have the list of default views and sheets and the level schedule. And now, after the execution of the process, we have all the floor planes, sailing planes, sheets, and levels scheduled. The second proposal concerns the development of a process allowing BIM coordinators to check the compliance of models to the BIM naming charter, especially when the project wasn't started with the previous process. Here is an example of BIM charter naming table with the one created for importing data into the model with all information concerning floor planes, including division, description, label, and the corresponding elevation. This process is based on 4 steps: entering the data in a single Excel file, importing it before extracting model view parameters to check finally compliance, and export the list of detected errors. The third proposal concerns structural engineers, allowing them to automate reinforcement rebar modeling, which is a complex task requiring a great mastery of modeling tools and a considerable amount of time. This work proposes to make reinforcement rebar modeling faster and more accessible by automating the process based on data from calculation notes. The process is based on 3 steps: entering data from the calculation note, importing reinforcement parameters, and finally generating the corresponding rebars. Another work has focused on developing a process that allows designers to set the number of coating tiles automatically and more accurately. To measure the coating in a project, architects calculate the covered surfaces and generally add 10 to 15 of cut. This method isn't precise and doesn't provide the exact amount of coating tiles to be used. Thus, this work proposes automatically calculating the number of whole tiles and offcuts and display the results in a table. This process is based on covering the shape's perimeter with an offset delimiting the entire tiles. The program checks the intersection between the tile's parameters and the offset line and thus calculates the number of total and partial tiles. The results are then extracted into an Excel table. The following proposal allows designers to automate the creation of commercial floor plans for real estate projects, which is a tedious mission to repeat for each apartment, for creating a sheet including the plan view and its location in the ground floor, and adding information about the apartment like the number, floor, saleable area. This procedure involves loss of time and risk of error. The proposed process starts with the generating all views planes by area plane with applying the same view template, then adding field regions with a visibility parameter that can be manipulated according to the apartment number, and finally creating shared parameters for all information to display. Here is shown an example of generated commercial floor plan after the execution of the process. A final proposal that concerns BIM coordinators and which allows them to automate 4D planning workflows. We know that 4D planning involves several tedious tasks to be applied to the project elements, like adding new shared parameter, ID parameter, to prepare construction tasks with source sets by category, by type, by level, etc., and to assign a construction date to each source set to simulate the building construction. This work proposes to automate the process through 3 steps. The first step concerns adding a construction task ID as a shared parameter for all project elements in one click, and then filling this parameter with values extracted from a prepared Excel file. The third step is to automate the creation of lists of project elements and then to attach a planning date to each list. Such a work approach makes it possible to optimize the process, save considerable time in configuration, and to facilitate access to 4D planning for any project. Finally, by discovering the potential of task automation to facilitate and transform our daily workflows, we become increasingly aware of the importance of optimizing our work processes. An ability to diagnose and discern repetitive and tedious tasks should now be developed to open up prospects for more optimized and efficient BIM approaches. Thank you for your attention, and do not hesitate to contact me in the mail below to learn more about optimizing processes.